Okay, so this is part two. Um, Part one did the first 10 problems. And we'll just go through 11 through 20. So define speed and velocity and use these definitions to explain why one of these quantities is a scalar and the other is a vector. So speed is, you should know this, is distance over time. And then velocity is displacement over time. So we can just plug these definitions into here, and then we have to use these definitions to explain why one of these quantities is a scalar and the other is a vector. So the reason why one of them is a scalar and the other is a vector is because distance has no direction. So if we divide a scalar by a scalar, in this case is time, this will also be a scalar. On another hand, if we have displacement does have a direction, so it has a positive and a negative. So then we have a vector divided by a scalar, which is equal to another vector. And that's essentially how you do number 11. It's just a simple definition. You basically have to memorize it. It's not very fun, but after a while you'll get used to it. On to the next quote. A boy throws a ball vertically upwards. It rises to a maximal height where it is momentarily at rest and then falls back to his hands. Which row gives acceleration of the ball at various stages in its motion? Take vertically upwards as positive, ignoring air resistance. So this one is actually really conceptual. After reading this problem, initially it might be a little bit confusing, but the only thing we need to do is imagine a velocity time graph. I should extend this a little bit more. So this is velocity and this is time. So we know that the boy throws the ball upwards. So we have initial velocity that is positive, but it's decreasing as it gets to the top, right? And then it finally hits 0 and it's temporarily at rest and it falls back down. So it has negative velocity. So now it wants us to give the acceleration of the ball at various stages in the motion. Well, we have rising, maximum height, and falling. So we have A here, B, and then C. But we know that acceleration is just the slope of the velocity graph, right? So that means the gradient is just G, or negative 8.91. In this case, all of the stages of motion is just negative 0.81 meters squared. Your next problem. A lorry travels at constant speed and then decelerates until it stops. Which graph shows a variation with time of distance traveled by the lorry? Okay. So we want to make sure that we have our definitions correct. So we have a distance graph. It's not displacement. So we're actually just going to see how far or how much distance the lorry travels. So lorry travels at constant speed and then decelerates. So that means that initially it is a straight line and then it tapers off into a slope of 0, because a slope of zero means that object is at rest. And since we look at this graph and then we look at B and then, wow, They're pretty much the same thing, so it is B. But even though it's B, what if you don't know like how to get to this graph? Like, how do you draw this graph on your own? Well, we can look at the other choices. So initially with A, you're actually accelerating here. But since the graph is going up like a parabola like this, that means it's concave up. So that means your object is actually accelerating, and then somehow you accelerate and then you just stop. And it doesn't really make that much sense in general, but that's why this is wrong. It's because it's actually accelerating when the problem says that it's decelerating. In terms of C, they actually like don't say that the lorry starts at a certain distance, and you can't really go down in a distance graph. That's only for displacement graphs. And thus the same reasoning applies for number D. So C and D are automatically off, and then A just does not make sense at all, so our final answer is B. So the displacement time graph for a toy car is shown, which graph shows the variation of the velocity of the car. So remember that velocity is change in displacement over time. So then our velocity graph should actually reflect the slope of each segment here. So if we look at this segment, 0 and 2, we can see that the slope is 2 up, 2 over. So rise over run, so 2 over 2 is equal to 1. And then we can just look at each graph, and then we have to just correspond it to each one. So first, we know that the first segment from 0 to 2 has a gradient 1. So that means V should be 1, like this one right here. So this one is impossible. B does not work. C does not work because the slope is positive, should be positive, and D might work. So then we look at the next segment, 2, 4, and we can clearly see that it's 0 because it's a straight line. And if we look at our two remaining choices, okay, they're both 0. So we move on. And then we have a negative slope. If you look at the answer choices, this one is negative and this one is positive. And since this one is negative, we don't have to calculate it. We can just say that it's A because this slope is negative, which is what we want. A football falls from the top of a tall building. Which graph best represents the way in which the distance x fallen varies with time t? Okay, so we have to take out the key information. So we know that it has to be a distance with time. So it's a distance time graph. And then we'll see what the answer choices look like. So this one decelerates and comes to a complete stop. This one has constant acceleration, and this one accelerates as it goes up. And then this one seemingly accelerates and then reaches terminal velocity. So in this case, it's actually going to be D. A does not work because as you're falling down, the force of gravity is actually pulling you down. So it's definitely not A. B, you don't go at a constant velocity, you accelerate of some kind. So it is not B. And then C, assuming there is air resistance, you eventually will reach terminal velocity, which is what D says. I believe that is the answer. It is D. Okay. A car X is traveling at constant speed U along a straight road. At time t equals 0, a second car Y is at distance d0 behind car X and traveling a speed at a speed of v in the same direction. Speed v is less than speed u. At time 0, car Y begins to accelerate with constant acceleration, and then car Y overtakes X at time t equals t, capital T. Which graph could best show the variation of time t with the distance d between the cars? Okay, so we can kind of try and break it up into two pieces. So let's say initially, right, our little Y car is traveling at a speed less than X. So momentarily, our distance is actually increasing, because if the person in front of you is accelerating, obviously they're going to be farther away. Okay, so now that we're actually accelerating, we can say that we're actually going up, right? This person is still going at the same speed, so that means our distance is actually decreasing. And these are the two main components. I did kind of forget, but something you should note, it should be 1.5 actually, is that at a certain point, we will be traveling at the same speed. So then D0 is momentarily not changing at all. I should say like the slope. No, actually, yeah, the slope. Yeah. So let's look at our graphs. So we know that momentarily increases, so we can automatically eliminate C and D because they don't increase for a little bit. And then as we see here, we have to see the concavity. So the main difference is that this goes down like that, while this one goes down like a waterfall, kind of. So we kind of know that as we accelerate, as our acceleration goes up, or as our speed goes up, sorry, not acceleration. Acceleration is constant in this case. As our speed increases, our D also decreases faster. So it actually becomes a steeper slope. In this case, I believe it is B. Yeah, because this actually is getting steeper in terms of like, oh, it's getting more negative. While in this case for A, it is actually becoming 0, which is not what we want. We want it to increase even more. State one similarity and one difference between distance and displacement. So one difference that you should always know is that distance is a scalar and displacement is a vector. State one similarity and one difference between, okay, so we have the difference and then now we need the similarity. So you can say that the SI units of both are in meters. It's kind of a somewhat dull moment, right? But this is generally, AICE doesn't really care about how easy it is. You just need to say it to them. Like they want that obvious, and this is how you say it. SI units of both distance and displacement are in meters. Yeah. So a student cycles uphill from home to his shop, taking 10 minutes. The student then spends 5 minutes in the shop before cycling home downhill at twice the initial speed. Which graph could show the variation with the time of distance traveled by the cyclist? So, distance. So we know that our graph is actually in times of distance. One thing you should generally know, I'm not sure if this is an actual definition, but this is how I imagine it, is that distance graphs are monotonically increasing. Oh god. Monotonically increasing. So this just means that at some point it's kind of like this and it goes up, whatever, but it will never go down in a negative slope. So in this case, like for example, let's take B. This one actually goes down and you can't travel a negative distance. Like that means that you're going back in time. Does that make sense? So B is not the answer. I don't know why I circled it. And the other is A. So it has to be C or D. And we know that from the problem, cycles uphill to the shop, taking 10 minutes. So that means that we stop at 10, and then we spend 5 minutes in the shop. So 5, we travel 0 meters. So it should be D. I know I said some fancy vocab, but just remember that in a distance graph, the distance will never decrease. It will either stay 0 or increase. Okay, number 19. An object falls from a tall building. The graph shows how the velocity of the object changes with time t. The acceleration of free fall is g. What describes acceleration of the object at time t equals y and t is equal to 0. So this is a similar problem from what we just did. Believe it was this one. So we noticed that our slope is always going to be negative. So our gradient is always going to be negative, and thus our acceleration is always going to be negative. But let's see how this works. So this is a velocity time graph, so it's not necessarily distance. And the graph shows how the velocity of the object changes. So we can just look at the slope of velocity, because the slope of velocity is equal to acceleration. If you haven't learned this, it's okay. This is part of particle motion of calculus AP. Yeah. So what is the acceleration of free fall is g, which describes the acceleration of the time. Okay. So our acceleration is always going to be constant if the acceleration is g, because the Earth does not change, it does not move, it doesn't change in mass, so thus our acceleration is always constant. And if we look at the graph at time t equals y, we're still increasing in velocity. So that means it's not 0, but it's going to be constant. So A and B, it says that acceleration is decreasing. That's not true. The Earth doesn't change in mass, so it doesn't change in its force, and thus gravity does not change. So it's always going to be constant. Remember that. And then at Z, t equals z, but our slope is going to be 0. This is because of air resistance. Although the force of gravity does never change, there is still an opposing force of air resistance that eventually slows you down to 0. In this case, z is when you already reach terminal velocity. So it's going to be d. Also, I should reiterate that at y, the object hasn't reached terminal velocity, so our acceleration is still constant. Okay, so immediately this one looks like a units problem. Yes, okay. So let's read the problem real quick. The drag force, F of D, is acting on sphere moving through a fluid, is given by the expression Fd equals kpv squared, where k is a constant, and p is the density of the fluid, and v is the speed of the sphere, blah, 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 blah. So we need the SI base units of k. So let's go ahead and first plug in each unit we actually know first. So force is a derived unit, which is just going to be newtons, and then you just use the equation F equals ma, force equals mass times acceleration. So force is newtons, and then mass is, oh god, kilograms, and acceleration is meters second to the -2. So then we have n is equal to k is what we want, p is the density of the fluid, so density is equal to mass over volume. So then we can say like capital D, I guess. Mass is kg divided by volume. So then capital D, and then v squared, so meters per second squared. And then now, since we have our kind of just our second step, we have to plug in our derived units over here. So newtons is kilograms, it's equal to k times kg, meters to -3rd times meters squared times s -2. So now, if we're now we just gotta like cancel out everything. This is gonna be fun. So we know that kg and kg will cancel out each other. This s -2 and s -2 will cancel out each other. And then we're left with k. We add these exponents because we're multiplying them and they have the same base unit. And then after that, we have k is equal to m squared. So our base unit is m squared. So the key for this problem is that you have to stay organized. I wrote these equations so I know exactly what I'm dealing with, and then we slowly plug everything in so we know where we are, and then we cancel out everything as we go along and rewriting as needed. For these types of problems, you want to minimize doing stuff in your head because you might blip over a single detail and then your answer will be wrong. So yeah, I guess that's it for the problems. This is vectors and introduction to kinematics. Thank you, I guess.